Today what we're going to be doing is starting section 2.3. This deals with real zeros of polynomial functions. And the first part of this section has us dividing, okay? Because that's really going to be helpful for us. One of the ways that we can divide is by long division. And in numbers 9 to 21 in the homework, that's what you guys are going to want to do. Please practice long division for here, okay? You guys remember how to do long division. I hope. If not, there are some examples in the book. I know that's something you guys did in Algebra 2, but I'll just kind of give you some words. When it asks us to divide 6x cubed minus 19x squared plus 16x minus 4 by x minus 2, this part right here is called our dividend. Okay. You are dividing that by x minus 2, and this x minus 2 is our divisor. And when you take the dividend divided by the divisor, you end up with our quotient. They say here that each of these are partial quotients that we get on the way. I'll just kind of talk you through this. Remember that we would take 6x squared times, you would start just by saying, okay, x goes into 6x cubed how many times? Don't even worry about the minus 2. Just look at the first term. And you'd say 6x squared. So you put that over the other x squared term. But then you multiply 6x squared by that whole divisor, x minus 2. And that gives us 6x cubed minus 12x squared. What then happens is then we subtract that. So we have to subtract 6x cubed, and then we subtract negative 12x squared. So we take 19x squared plus 12x squared. That gives us negative 7x squared. Then we bring down the next part of the dividend, and we just repeat that process. In this case, there is no remainder that's there, so we don't have anything to write on the side, but essentially that's how we can use long division to divide functions, okay? Let's do the same question, but use synthetic division instead. And the synthetic division is what they ask you to practice in numbers 23 to 31. And to be honest, we'll be getting lots of practice with that synthetic division. But if we wanted to divide 6x cubed by minus 19x squared plus 16x minus 4 by x minus 2, remember what we're going to do is we're going to take all of the coefficients of our dividend. If there are ever any missing degrees, we would put a 0 in place of that, but there isn't. And we put those coefficients up here, and now we want to divide by x minus 2. So over here to the left, we're going to put the x value that would make that 0. So that is 2. Sorry. And then we do this type of a process. We bring down the first term, and then we multiply 6 times 2 to get 12. And then in synthetic division, we add. We've already changed this sign, essentially. So that means we've already compensated for that subtraction, so we can just add. So I get negative 7. Do the same thing. Negative 7 times 2 is negative 14. And then I add to get 2. 2 times 2 is 4. And I add to get 0. And again, this here just means that there is no remainder. Now, our answer isn't 6, negative 7, 2. What we're doing is we're trying to divide. We're dividing this 6x cubed and all this other stuff by x minus 2. And when we think about dividing 6x cubed by x, we can see that we're going to decrease that power by 1 since we would subtract our exponents. And so we can only use synthetic division with these linear factors. If this was x squared minus 2, we wouldn't be able to use synthetic. We'd have to use long division. And so what that means is that this 6 is going to be the coefficient of x squared. And then we'd have minus 7. Negative 7 is the coefficient of x. And then we have positive 2 as our constant. Okay? And again, there is no remainder. Okay? Hopefully you guys remember that. Well, that remainder that's obtained in that synthetic division process has an important interpretation, and that's described in the remainder theorem. What this says is that if a polynomial, f of x, is divided by x minus k, then the remainder is r equals f of k. What that does is the remainder theorem tells you that synthetic division can be used to evaluate a polynomial function. That means that to evaluate a polynomial function f of x when x equals k, all we do is we divide f of x by x minus k, and the remainder will be f of k. Let's do that in this example 1. This says to use synthetic division to find the function value. We have f of x equals 4x cubed minus 13x plus 10, and it wants us to find f of 2. Negative 2, my bad. So what we can do is we can use synthetic division to help us evaluate instead of substituting negative 2 in. And you might say, well, why would I do this? Well, I don't know. There's kind of a lot of powers and like order of operations that you have to follow if you substitute this in. But using the synthetic division, all we're doing is multiplying and adding. It's really nice. So let's start with the coefficient 4. Notice we're missing a degree. X squared is missing a degree, so we're going to put a 0 in there. Negative 13, 10, and then that's our constant, so we're all set. We do want to find f of negative 2. Negative 2 is the x value, so we do not change the sign like we did when we were dividing by the expression. So we'll put that negative 2 in, and then we'll do that process of synthetic division. So we'll bring down the 4. We're going to multiply and add, multiply and add, multiply and add. That's not too bad. And what this is telling us is that this is our remainder. And that's telling us what our function value is. And I'd like you to write it like that. Don't just put 4. Put that f of negative 2 is 4. That's what you were really evaluating. That's kind of the beauty of that. You're saying that when the input is negative 2, I'm getting 4 as my answer. Okay? So that's how you could do something to use synthetic division to find the function value. And again, if it says to use synthetic division, make sure that we try to do that and follow those directives, okay? So another important theorem is this factor theorem. This factor theorem says that you can test whether a polynomial has x minus k as a factor by evaluating the polynomial at f of k. If your result is 0, which means if you get a remainder of 0, then x minus k is a factor. Okay? So this f of negative 2 that we did in example 1, that would correspond to the divisor x plus 2. Because there was a remainder here, that means that x plus 2 is not a factor of this polynomial. Okay? Let's look at example 2, and we'll see when we will find a factor. This says to use synthetic division to show that x is a solution of the third degree polynomial equation. That's what we're going to do first. And then we'll use the result to factor the polynomial completely. Okay? So here is our third degree polynomial, x cubed minus 28x minus 48 equals 0. And it's telling us that x equals -4 is a solution. So what that means is that that should go in evenly, which means we have a remainder of 0. So let's try that out. So we'll use our coefficients. 1 is our coefficient of x cubed. Ooh, again, there's no x squared term, so we'll use 0. -28 and -48. Okay. And x equals -4 is the value that we'll use here. So we're going to bring down our 1, multiply, and add. Multiply, and add. Multiply, and add. And happily, it is, all right? And so in letter A, it's asking us to show that this is a solution. So really, this is what is showing that it's the solution. I'm going to say the remainder is 0. So x equals -4 is a solution. Okay. That's really the justification behind that. The remainder is 0, so we know that this is a solution. That's how you use synthetic division to show that you have a solution that's there. Okay. Well, now let's use the result to factor the polynomial completely. So we'll do that here. Okay. So let's have our f of x. Okay. I know I didn't name it that, but here, we'll just have f of x equals. And then let's see what we have. Each of these are going to be pieces that are going to be multiplying together. Because again, here was our dividend, here was our divisor, and here was our quotient. Now, our divisor wasn't really -4. Our divisor was really x plus 4, wasn't it? Because that's the expression that if we said that x equals -4, then we end up getting x plus 4 as that divisor. Okay. And then here we have our quotient. X cubed was here. And again, because we're dividing by a linear divisor, that means this is going to end up being x squared. So this ends up being 1x squared minus 4x minus 12. And again, this was the quotient part. Okay. I don't know if you need to make a note here that, again, this part helped us with the divisor and this part helped us with the quotient. Okay. Now it asks us then to factor this completely. X plus 4 can't be factored any further, but could this be factored any further? Okay, let's see. I can try x and x, and you guys probably already see that that can be x minus 6 and x plus 2. And so this will be my result for that completely factored polynomial. F of x equals x plus 4 times the quantity x minus 6 times the quantity x plus 2. That's completely factored. Okay? All right. So the next example asks us to verify the given factors of the function, then to find the remaining factors of f, and then use our results to find the complete factorization of f. Okay? So they want us to verify the given factors. They give us this polynomial, this quartic polynomial, and then they have these different factors. So let's start by verifying x plus 2. We're going to start with the polynomial itself and use synthetic division to do so. So we've got 8, -14, -71, -10, and 24. Okay, so we've got those as our coefficients. Because we're dealing with x plus 2, that is eluding to the 0, x equals -2. So we'll use that here. And we are going to bring down 8. We're going to multiply and add. Multiply and add. Multiply and add. Multiply and add. And because of that, we can see that x plus 2 is verified. Okay, we have verified x plus 2 as a factor because we ended up getting 0 as that remainder. Now, when I verify x minus 4, you guys, let's not use the original one, okay? One thing that we can do is we can use what's called the depressed polynomial. Don't worry, it's not sad. It's just 1 degree less than the other one. And the depressed polynomial is going to have these as our coefficients. So instead of going way back to the original polynomial, let's use the depressed polynomial to verify this next factor. Okay, so to verify that x minus 4 is a factor, that corresponds to x equals 4. And so we're going to bring down the 8. We're going to multiply and add. Multiply and add. Multiply and add. And we've now verified that x minus 4 is a factor because our remainder was 0. Now you might say, why would you use the depressed polynomial? Well, you guys, because let's take a look at what we have created with all of this. What we've created with all of this is that we had a polynomial that was x to the 4th. We then had a polynomial that was x cubed. And now we have a polynomial that's x squared. That's a quadratic. And the nice thing about quadratics is that quadratics are pretty nice for us to factor. And even if we can't factor a quadratic, if we wanted to solve, we can still solve quadratics using things like the quadratic formula. All right, so that's kind of why we use the depressed polynomial, because our goal is to get it to a quadratic so that we can eventually figure out what the other zeros will be in time, okay? So this asks us to verify the given factors of the function. We did that. Now it tells us to find the remaining factors of f, and that's what we're going to be doing here. This is the other factor of f. So let's see if we can factor that at all. So 8x squared plus 2x minus 3. I'm probably going to try 4x and 2x because those are kind of in the middle. And if I do 3 and 1, that gives me 6 and -4. So that would be those would be the other factors, okay? And now it's asking us to use our results to write the complete factorization of f. And so we can say that f of x is going to be x plus 2 x minus 4, and now these other factors, 4x plus 3 and 2x minus 1. Okay, and those are our remaining, that is the complete factorization. So we use these two factors, and then we also used the other factors that we had found. Okay, now here's the scoop. I just want to, because of what the next video is like, I do want to talk to you guys a little bit about the next piece of this. That should be fine for your homework for tonight. On the second day's homework, what we do is we start talking about the rational zero test, which again isn't new, okay? The rational zero test just says that if our polynomial f of x equals, and then we have this polynomial, has integer coefficients, then every rational zero of f has this form p over q. So we'll end up talking about that a little bit more on our next lesson. I will give you guys this time to start the assignment. Okay, sound good? So thanks for listening. You guys have a great day.